Okay, good morning. Welcome to
FamilyMath173a.
FamilyMath173a and to infinity and
To the next infinity.
what? There's another infinity.
Where?
Wah. Well, we had a very interesting week. We were studying a little bit about geometry, and we had a plane and a circle, and you asked a really neat question. And what was that question?
Are there more lines that pass through the circle or don't pass through the circle?
Are there more lines that pass through the circle in the plane, or that don't pass through the circle in the plane? So it didn't really matter how big the circle was, because however big it is compared to the whole plane, it's going to seem pretty small.
Yeah.
Right, what do you think about this question?
I think it's going to be the same.
Okay, how come?
Well, because the circle is infinite points, and you can attach a line to two of those points, and infinity divided by 2 is infinity.
Ooh, interesting. Okay. What do you think?
Well, yeah, because it probably is going to be the same. You have infinity points. The circle has infinity points, but the rest of the plane also has infinity points.
So infinity equals infinity.
Yeah.
Interesting. Well, this turns out to be not just a really cool question. This turns out to be, this kind of question was something that some mathematicians spent a long time thinking about, especially in the late 1800s. And one in particular, Georg Cantor, really spent a lot of time studying infinity. You okay?
Yep.
Yep. So, Cantor discovered that there are different kinds of infinity. Sorry, the board's not erasing too well. So the smallest, the quote, smallest infinity is just the counting numbers that you know. 1, 2, 3, 4, 5, 6, all the way up to, eventually you will get to...
Infinity.
Really?
No.
No.
It will take forever.
Yeah, you won't ever actually get there. But this is the first infinity, the smallest infinity. Sometimes people write it as aleph null, sometimes people just write it as infinity. And this infinity has some surprising properties. So for example, if I look at just the even numbers, seems like this set is smaller than that set. How come?
Well, there's half as many numbers.
It looks like you're just taking, because you're just taking the 2, the 4, the 6.
Right, so like 1 I just threw away,
Yeah.
3 I just threw away, 5 I just threw away.
Yeah.
Okay? And so you might intuitively say, hey, there's half as many numbers in this list.
Yeah.
And this is where Cantor had some really interesting ideas. So what Cantor said is, if I can find a map that goes from this set to this set in a one-to-one way, so one number goes to one number. It might not, like 1 might go to 6, and 2 might go to 2, and 3 might go to 8, or 10, whatever. But as long as one number goes to one number this way, and then I can do something in reverse, one number going to one number this way,
Yeah.
then those two sets are going to be the same.
So here, if you multiply by 2, it goes to a certain. If it goes to one number in this sequence, goes to a number in that sequence.
Yeah, that's pretty interesting. So going from this set into this set turns out to be not super hard to do.
Yeah.
You just even said, what do I do?
You multiply by 2.
Okay, so 3 goes to where?
6.
6 goes to?
12.
Okay, so I can see how to go this way in a one-to-one way. One number here goes to one number down here.
Yeah.
Okay, now can I do it in reverse? Can I take one number here and send it to one number here in an easy way?
All you have to do is divide by 2.
Okay, so where does 6 go to?
3.
Where does 4 go to?
2.
2. Where does 12 go to?
6.
Where does 500 go to?
250.
Aha. So there's this bijection, is what that's called. We can go this way and that way, and every number goes somewhere, and no number goes to the same number.
Yeah.
And so Cantor said, in that case, we're going to say these two sets have the same size.
Wow.
So you wouldn't think that would have the same size as this one,
No.
Yeah.
but it does.
Wow.
All right, you ready for a slightly more challenging one?
Yeah.
All right, so we'll go to the next one.